Section 13.6 Colloids. When finely divided clay particles are dispersed throughout water, they eventually settle out of the water because of gravity. The dispersed clay particles are much larger than most molecules and consist of many thousands or even millions of atoms. In contrast, the dispersed particles of a solution of a molecular size. Between these extremes lie dispersed particles that are larger than typical molecules, but not so large as the components of the mixture separate under the influence of gravity. These intermediate types of dispersions or suspensions are called colloidal dispersions, or simply colloids. Colloids form the dividing line between solutions and heterogeneous mixtures. Like solutions, colloids can be gases, liquids, or solids. Examples of each are listed in Table 13.6. The size of the dispersed particles is used to classify a mixture as a colloid. Colloid particles range in diameter from approximately 5 to 1,000 nanometers. Solute particles are smaller. The colloid particle may consist of many atoms, ions, or molecules, or may even be a single giant molecule. The hemoglobin molecule, for example, which carries oxygen in blood, has a molecular dimensions of 65 angstroms and a molar mass of 64,500 grams per mole. Although colloid particles may be so small that the dispersion appears uniform even under a microscope, they are large enough to scatter light very effectively. Consequently, most colloids appear cloudy or opaque unless they are very dilute. Homogenized milk is a colloid. Furthermore, because they scatter light, a light beam can be seen as it passes through the colloidal suspension, as shown in Figure 13.26. This scattering of light by colloidal particles, known as the Tyndall Effect, makes it possible to see the beam of light of an automobile on a dusty dirt road, or the sunlight coming through a forest canopy. Not all wavelengths are scattered to the same extent. As a result, brilliant red sunsets are seen when the sun is near the horizon and the air contains dust, smoke, or other particles of colloidal size. Hydrophilic and hydrophobic colloids. The most important colloids are those in which the dispensing medium is water. These colloids may be hydrophilic, water-loving, or hydrophobic, water-fearing. Hydrophilic colloids are most like the solutions that we have previously examined. In the human body, the extremely large molecules that make up the important substances as enzymes and antibodies are kept in suspension by interacting with surrounding water molecules. The molecules fold in such a way that the hydrophobic groups are away from the water molecules, while on the inside of the folded molecule, where the hydrophilic polar groups are on the surface interacting with the water molecules. These hydrophilic groups generally contain oxygen or nitrogen and often carry a charge. Some examples are shown in Figure 13.28. Hydrophobic colloids can be prepared in water only if they are stabilized in some way. Otherwise, their natural lack of affinity for water causes them to separate from the water. Hydrophobic colloids can be stabilized by absorption of ions on their surface, as shown in Figure 13.29. Adsorption means to adhere to a surface. It differs from absorption, which means to pass into the interior, as when a sponge absorbs water. These adsorbed ions can interact with water, thereby stabilizing the colloid. At the same time, the mutual repulsion between the colloid molecules with adsorbed ions of the same charge keeps particles from colliding and getting larger. Hydrophobic colloids can also be stabilized by the presence of hydrophilic groups on their surfaces. Small droplets of oil are hydrophobic, for example, so they do not remain suspended in water. Instead, they aggregate, forming an oil slick on the surface of the water. Sodium stearate, or any similar substance having one end that's hydrophilic, polar or charged, and one that's hydrophobic, nonpolar, will stabilize in a suspension of an oil in water. Stabilization results from the interaction of the hydrophobic ends, the stearate ions, with the oil droplet, and the hydrophilic ends with the water, as shown in Figure 13.31. Figure 13.29, Hydrophobic colloids. Schematic illustration of how adsorbed ions stabilize a hydrophobic colloid in water. The stabilization of colloids has an interesting application in our own digestive system. When fats in our diets reach the small intestine, a hormone causes the gallbladder to excrete a fluid called bile. Among the components of bile are compounds that have chemical structures similar to sodium stearate. That is, they have a hydrophobic polar end and a hydrophobic nonpolar end. These compounds emulsify the fats present in the intestines and thus permit digestion and absorption of soluble vitamins through the intestinal wall. The term emulsify means to form an emulsion, a suspension of one liquid in another, as in milk, for example. An example that aids in the formation of an emulsion is called an emulsifying agent. If you read the labels on food and other materials, you'll find that a variety of chemicals are used as emulsifying agents. These chemicals typically have a hydrophilic end and a hydrophobic end. Removal of colloidal particles. Colloidal particles frequently must be removed from a dispensing medium, as the removal of a smoke from smokestacks or butterfat from milk. Because colloidal particles are so small, they can't be separated by simple filtration. Instead, the colloidal particles must be enlarged in a process called coagulation. The resultant larger particles can then be separated by filtration or merely by allowing them to settle out of the dispersing medium. Heating the mixture or adding an electrolyte may bring about coagulation. Heating the colloidal dispersion increases the particle motion so that the number of collisions. The particles increase in size as they stick together after colliding. The addition of electrolytes neutralizes the surface charges of the particles, thereby removing the electrostatic repulsions that prevent them from coming together. Wherever rivers empty into oceans or other salty bodies of water, for example, the suspended clay in the river is deposited as a delta when it mixes with the electrolytes in the salt water. Semipermeable membranes can also be used to separate ions from colloidal particles because ions pass through the membrane of the colloidal particles cannot. This type of separation is known as dialysis and is used to purify blood in artificial kidney machines. Our kidneys normally remove the waste products of metabolism from blood. In a kidney machine, blood is circulated through a dialyzing tube immersed in a washing solution. The washing solution contains the same concentrations and kinds of ions as blood, but is lacking the molecule and ions that are waste products. Waste therefore dialyzes out of the blood, but the ions and the large colloidal particles, such as proteins, do not.